Hello there. Here is an example that deals with um, the sampling distribution of the sample proportion. Excuse me. This is related to the sampling distribution of the sample mean, um, but while it's related, it's worth looking at it its own unique example here. So suppose we have this scenario where we're at a lake, and we know, I just made this number up, but we know that 40% of the fish in this lake are bass, or in other words, P is 0.4. Okay, if P is the proportion of bass in the lake. Now, suppose further that someone goes and gathers 100 fish through a random sample, and we ask the question, before we go get the fish, what is the chance that we get a sample proportion of bass that will differ from the population proportion by more than 5%? Okay, so the question we're asking here is if P is 0.4 and N is 100, then what is this probability? What is the probability that the sample proportion, that is P hat, differs from the population proportion? Now, when we say differ, we don't just mean P hat minus P is bigger than 5%, rather that the difference, or the absolute difference here, is greater than 5%, or that the absolute value of P hat minus P is greater than 0.05. So that's the probability we're after. Well, we actually know that this is 0.04, so we'll plug that in later, because P is 0.04 that we've discovered from the problem. Now, in order to compute the probability, a probability about a random variable, in this case the random variable is P hat. It is yet to be observed. We will observe P hat as soon as we gather our sample and figure out how many bass out of that 100 figure out how many fish out of that 100 are in fact bass. That will give us what P hat is. But we haven't observed that yet, so again, it's a random variable. To compute the probability about a random variable, we need to know its distribution. Well, we know a little bit about it. If you've been reading in your text and online, you know that by the central limit theorem, P hat is approximately normal if we have a sufficiently large sample. And for us, for your textbook, what we're saying here, sufficiently large sample, is that N times P is greater than or equal to 5, and N times 1 minus P is greater than or equal to 5. Okay, that's the textbook's view of a sufficiently large sample. Okay, now, so is this true? Is that true? Well, let's see here. N times P for us is 100 times P is 0.04. I'm sorry, not 0.04. That is not 0.04. That is 0.4. Made a mistake there. All right, 100 times 0.4, that is 40. Okay, and that is in fact greater than 5, so this inequality checks out. What about N times 1 minus P? N times 1 minus P is 100 times 1 minus 0.4. That's 100 times 0.6, which is 60, and that is also greater than 0.5. And so these do work out. So we do have a sufficiently large sample. So thus, P hat is approximately normal and I'm going to go ahead and specify the mean and the standard deviation of P hat. So the mean here, if you recall, is represented with mu sub p hat, and that turns out to be just the population proportion. And the way we think about this quantity here is, if I was to take if I was to repeatedly take samples of size 100, and each sample I would have a sample proportion, what's the average of all those sample proportions? That's what this number is here. And it turns out that mathematically, that is just the population proportion. And for us, for this problem, that is 0.4. Okay? And the other quantity we need to know is the standard error of p hat, or sigma sub p hat, or also called the standard deviation of p hat. That is the square root of p times 1 minus p over n. Okay, so just plugging in the right values of p and n here, we get the square root of 0.4 times 1 minus 0.4 over 100, and that is, so I've got 0.4 times 0.6, that's 0.24 divided by 100, that's 0.0024. Take the square root of that, and it turns out you get 0.0490. We'll go with that, 4 decimal points there. So okay, now I know something about the distribution of p hat. So when I come back to what I originally wanted to do is compute this probability, I'll apply this principle here. So I've got the probability that p hat minus p is greater than 0.05. I'm just rewriting it. That is equal to the probability. I'm going to plug in 0.4 here. I know p is 0.4 for this problem. And so that's what we get so far. Now, the way I think about this absolute value is a little bit tricky here. I got to be careful with it. P hat minus 0.4 can be greater than 0.05 when p hat minus 0.4. I'm sorry, the absolute value of p hat minus 0.4 can be greater than 0.05 when p hat minus 0.4 is greater than 0.05, or when the negative of this quantity in here is greater than 0.05, which is equivalent to 0.4 minus p hat being greater than 0.05. Okay? So if this event happens or if this event happens, then that's equivalent to the absolute value of p hat minus 0.4 being greater than 0.05. All right. Well, this event is exclusive of this event, so I can write this as the sum of these two, right? So one of the probability rules, if I have an event in the union, the OR can be thought of as the union. If I've got, say, an event A, union an event B, and I take the probability, that's the probability of A plus the probability of B, and I don't have to contend with the probability of the intersection. Okay, so what I've got here on the left-hand side is this probability I need to work with. Well, it turns out, and I'm pretty close here, I've got p hat minus, this is P, right, 0.4 is P, and what I know, I'm going to do this on the side here, what I know is that this quantity p hat minus P over the square root of P times 1 minus P over N, that is a standard normal variable, or approximately a standard normal variable. If I go through this transformation, I am standardizing p hat. Well, I've done the numerator of it. I've got p hat minus P, the P is 0.4. I just got to divide by this square root term to fully get a Z. So I'm going to have p hat minus 0.4 over the square root of 0.4 times 1 minus 0.4 over 100. This is greater than what I've done to the right hand side. I'm going to do to the what I've done to the left-hand side, I'm going to do the right-hand side. So I've got 0.05 divided by that same square root term, which, by the way, I've already computed, but I'm just rewriting it here. Okay. That is the first probability. This probability here, I'm going to rewrite this. I want this in the form of p hat minus a number. So if I do that, I can have p hat minus 0.04, minus 0.4. But to do that, I have to multiply this by -1. And if I do that, I've got to multiply the other side by -1 and flip the inequality. So I've got less than -0.05. Okay. So I'm going to simplify here. I've got the probability that z is greater than, on the right-hand side, this is 0.05 divided by the square root term, or 0.05 divided by this number here, which we already computed. So 0.05 divided by 0.049 is 1.02. Now I've got to come back to here. I've got a little more work to do with this probability here. This is a probability. Again, I want it to look like, I wanted something in this form so that I can have a z. Well, I've got p hat minus 0.4. I've got the numerator of this form. But if I divide by the square root term, I will have the form that I need here. So divide by the square root of 0.4 times 1 minus 0.4 over 100. And that is less than -0.05 divided by the same term. 0.4 times 1 minus 0.4 over 100. And I'll take the square root of all that. Okay, so a lot of work here. Oh, gotta catch my breath. But we're almost there. So this is the probability that z is greater than 1.02 plus the probability right here, that becomes a z. This is, well, it's no surprise, this is the negative of what this number is. So this is negative 1.02. Okay, so can I compute these two probabilities here? That's the question. I'm going to actually flip over the page here. I'm running out of space. So I've got the probability that z is greater than 1.02 plus the probability that z is less than -1.02. Yes, I think, yes, that's correct. Okay. So I'm going to draw a picture here for both probabilities. Here, say for the first one, I've got 1.02. And so this is the area I need right here. Okay, that's what I'm after. Well, I know from table C in your textbook, you can see from table C the area to the left of 1.02. This is something we've done before, so I'm not going to show it to you. That area is 0.8461. So this is 0.8461. So this is 1 minus 0.8461. That is the shaded area. 1 minus 0.8461 is 1539. So when I come up here, this is 0.1539. Okay. I'm going to add that to whatever this probability is. Well, I'm going to have to draw a picture for that as well. So here's my standard normal plot. So I've got -1.02, and I want the area under the curve to the left of that. All right, that's my area. Well, let's see. Do I have to go look at a table again to get this area? Well, actually we don't, because if we look at this picture here, and we can use this picture and what we've done here to get what we need for here. Let me convince you. The area under the curve to the right of 1.02, it turns out, is equal to the area under the curve to the left of -1.02. And the reason is because this curve is symmetric about 0, so these areas there would be the same. Well, I know this area is 0.1539. I just found it. So the area under the curve here is 0.1539. So coming up here, we've got 0.1539. Multiply that times 2, and I get 3078. So what this is saying basically is there's a little over a 30% chance that you would go out and sample 100 fish and see the proportion of bass that is further away from 0.4 by at least 5%. Okay. I hope this was helpful.